Hello everyone. We have seen in the previous video how we can represent the vector in Cartesian coordinates, and we have seen that the vector can be represented as x component in x direction, y component in y direction, and z component at z direction. Now we are going to mention what is meant by vector field. The vector field is field quantity which represent or which depends on the coordinates x, y, z, which can be represented as r as a vector. And this function itself is vector quantity. So it can be represented as x component vx in x direction, vy in y direction, and vz in z direction. And each component is a function of the space, it's function of x and y and z. And it is not mandatory, or it is not sufficient, or it is not required. It is not required that if I'm talking about Vx, it depends on x. It can be depending on y or on z. And it also can depend on x. So effectively, the function Vx is function of x, y, and z, but it is in the direction of x. The function Vy is a function of x, y, and z, but it is in direction of y. And the function Vz is a function of x, y, and z, but it is in direction of z. As an example, assume that V is 2 multiplied by e to the power z over 100 in direction of x. So in this case, the value of Vx is 2 multiplied by e to the power z over 100. It is function of z only, but it is in the direction of x. That's what we are seeing vector field. The products of the vectors, we have two types of products. We have dot products and cross product. Dot product, or in other words, it is scalar product of the vectors. If I have two vectors a and b, and we are assuming the dot product of them is the modulus of the vector a multiplied by the modulus of the vector b multiplied by the cosine of the angle between them, cosine theta ab. Dot product or scalar product is used, for example, in calculating the work. So if we have force and displacement, so the force dot the displacement equal the work done. And this can be represented as the magnitude of the force, the magnitude of the displacement, and multiplied by the cosine, the angle between the force and the displacement. If we are talking about Cartesian coordinates, for example, the x and y and z components are orthogonal to each other. So the angle between x and y is 90 degrees, and the angle between y and z is 90 degrees, and the angle between z and x is 90 degrees. So if you are talking about the dot product between x component and y component, it would be 0, because cosine 90 is 0. So if I'm talking about the dot product between a and b in Cartesian coordinates, we can represent a in Cartesian coordinates as ax in x direction plus ay in y direction plus az in z direction, and similarly bx in x direction, by in y direction, and bz in z direction. So the dot product between a and b in this case would be ax in x direction dot bx in x direction. So in this case, ax dot ax would equal the magnitude of ax, which is unity, multiplied by the magnitude of ax, which is unity, multiplied by cosine the angle between them, AX and AX, the angle between them is 0, so cosine 0. Cosine 0 is 1, so this AX multiplied by BX. Now, if I'm talking about AX multiplied by BY, the unit vector AX multiplied by unit vector AY would be 1 multiplied by 1 by cosine multiplied by cosine 90. So it is 0. So AX multiplied by BY would be 0. Similarly, AX multiplied by BZ would be 0. Now, if I'm talking about AY multiplied by BX, it would be 0. AY multiplied by BY would be AY BY. AY multiplied by BZ, it would be 0. Finally, AZ multiplied by BX would be 0. AZ multiplied by BY 0. AZ multiplied by BZ, it would be AZ plus BZ. So the dot product in Cartesian coordinates between A and B, A dot B would be the x component of A multiplied by the x component of B plus the y component of A multiplied by the y component of B plus the z component of A multiplied by the z component of B. If I'm talking about A dot A, so it would be AX squared plus AY squared plus AZ squared, which effectively the magnitude of A squared or the modulus of A squared. If I'm talking about unit vector multiplied by itself, so the unit vector in A direction multiplied by the unit vector in A direction would be 1 multiplied by 1 multiplied by cosine the angle between them, so cosine 0. So 1 multiplied by 1 cosine 0, which is 1, so to equal 1. So the unit vector, any unit vector multiplied dot product by itself equals 1. It should be noted that A dot B equals B dot A. So it doesn't depend on the arrangement between the dot product. If we are saying that B dot AX and we see that B is Bx in x direction, By in y direction, Bz in z direction, so only the x component will contribute to this one. So in this case, Bx multiplied by Ax dot Ax, it would be Bx. So effectively, the dot product of B multiplied dot product by the unit vector of Ax is the projection of the vector B in the direction of Ax. Or in other words, if I'm talking about any direction A, B dot A is the projection of the vector B in the direction of the unit vector A. So B dot A equals the magnitude of B multiplied by the magnitude of A multiplied by the cosine of the angle between them. Magnitude of A is 1, the unit vector, so B cosine theta is the projection of B on the direction. Assuming that we have a normal light coming from the up, so the shadow of V on the direction of A is this projection. The other type of vector product is the cross product or the vector product. In the vector product, if we are saying that A cross B, it would be a vector quantity, its direction in the n direction, which is a normal to both A and B. So assuming that we have the vector A and the vector B, the normal to the plane containing the two vectors A and B is a vector n. So the cross product is a vector quantity normal to both A and B, and its magnitude is the modulus of A multiplied by the modulus of B multiplied by the sine of the angle between A and B. So sine theta AB. And the direction of the normal depends on the right hand rule. So assuming that we are going with a screw using the right hand rule, so the direction would be in a similar way, like this. Okay, so if I'm talking about A cross B, I'm moving by my right hand from A to B, this would be the direction of the norm. So if we replace A and B such that we are talking about B cross A, so in this case, I'm using my right hand starting from B to A. So in this case, the normal direction would be in the opposite direction. So in this case, the cross product B cross A as a magnitude would be the same as A cross B, but as a direction, it would be in the opposite direction, so it would be the negative value of A cross B. Now, if we are going to make the cross product for the basic unit vector of the Cartesian coordinates, if we are talking about AX cross AY, so according to the right hand rule, if I'm moving from AX to AY, I'll be in the Z direction. And as a magnitude, this one multiplied by 1 and cosine the angle between them is 90 degree, sine the angle between them 90 degree. So 1 multiplied by 1 multiplied by sine 90, it is 1 in the Z direction. So AX cross AY would equal AZ. Similarly, we can find out AY cross AZ would equal AX. And finally, AZ cross AX would be AY. Now, if we have changed the arrangement, so we are saying AY cross AY cross AX would be minus AZ cross AZ cross AY would be minus AX, and AX cross AX cross AZ would be minus AY. Okay? So, if I have two vectors, A and B, and both of them are represented in Cartesian coordinates, such that the vector A has AX in X component, AY in Y component, AZ and Z component, and similarly the vector B. And I want to find out the cross product between A cross B. So in this case, I'm going to make the cross product starting from AX to BX, AX to BY, AX to BZ, AX cross AX. Now the angle between AX and AX is 0. And we have seen that the cross product is proportional to the sine of the angle between the two vectors. So sine 0 equals 0. So AX cross BX would be 0. Now AX cross BY. AX cross AY would be AZ. So AX multiplied by BY in the direction Z. AX multiplied by BY multiplied by AX cross AY, this would be AZ. Similarly, AX cross BZ would be multiplied by AX cross AZ, that would be minus AY. So, in a similar way, we can find out the multiplication of AY with the different components of B and AZ with the different component of B. So, if we make all this combination, we have 9 combinations. 3 of them are 0 because AX cross AX is 0, AY cross AY is 0, AZ cross AZ is 0. And the remaining 6 components would be as follows: AY multiplied by BZ minus AZ multiplied by BY in X direction, AZ multiplied by BX minus AX multiplied by BZ in Y direction, plus AX multiplied by BY minus AY multiplied by BX in Z direction. I'll make just one of them and you can complete the remaining. Here, if I'm talking about here AX cross AX is 0, AX cross BY, AX cross AY would be AZ. So this component AX multiplied by BY in z direction. And similar to it is each component, this component ay cross ax, and we have said that if ax cross ay is az, so ay cross ax would be minus az. So this component would be ay multiplied by bx in the direction of minus az. So by taking az as a common factor and taking into consideration this is minus az, not az, so in this case the z component would be ax by minus ay bx in z direction. You can follow up the remaining parts to find the x component and the y component. Okay? We can make this multiplication in a simpler determinant form. So a cross b, it can be represented as the unit vectors ax, ay, ez, and the x component of a, x component or y component of a, z component of a, and finally b component of x component of b, y component of b, and z component of b. Now, by taking the determinant, I'll take also the z component. We can find the z component here. Here positive, negative, positive. So positive az multiplied by ax by minus ay bx. Ax by minus ay bx in the direction. You can complete the remaining part ax, ay, and you can compare this formula with the previous formula obtained in the previous slide. You find out the determinant is quite sufficient to obtain the cross-vector product of the two vectors in Cartesian coordinates. Okay.